shows as built specimen without retrofit. Blue shows with retrofit, without anchors. Red shows with anchors. So without anchors, it failed under about 1,000 kilogram of TNT at 30 meters. But when we used anchors, we went up to more than 23 kilograms of TNT at about the same distance. So the lesson to take home is that these anchors do work in terms of preventing pond failure. We then extended the project to two-way slabs, and we tested them under one way in this case, and we covered them with FRP. There's a significant increase. In fact, we exceeded the capacity. We couldn't fail, so then we increased duration to increase impulse, and at 100 kPa and 2500 kPa millisecond of impulse, we significantly increased the capacity. And after the test, we removed the FRP to see what happened into the concrete. You can see a whole bunch of series of flexural cracks. And then we did URM infill walls. So if you have unreinforced infill walls, in the previous test program shown by the previous speaker showed a very good example of infill use. And these infill walls are meant to be non-structural, and they are supposed to remain non-structural. During earthquakes, in order for them not to participate, we leave some gaps. The Canadian National Building Code says you have to either isolate or integrate. If you integrate them with the enclosing frame, then you have to design them as shear walls. Otherwise, you have to leave some space for a frame to displace without being interfered by the URM wall. However, in practice, it never happens that way. In this case, because of that, there is supposed to be a gap at the top to allow settlement or deflection of the slab. But as a retrofit measure, we filled that so that arching action can develop. So these walls cannot fail if arching develops. In fact, arching increases capacity tremendously. When the wall wants to fail, it has to expand in the longitudinal direction, but there's no gap, so then frame would provide arching action. As you can see, even though it's unreinforced, this compression force and that compression force would leave around would provide some moment resistance. So if you test an infill wall, this is under very slow motion, this is how it fails, and its capacity is very, very limited. In fact, we had problem keeping it in place because these were scaled down units. We then used FRP. The capacity went up significantly, and there was control of cracking, which can control displacements. Then arching action increased with increased capacity. Eventually we failed it, but then it failed as one piece, and there was fragment control, because in masonry walls, bits and pieces of fragments flying in become very lethal. And then we tried another retrofit technique, which is polyurea, spray on polyurea. This is the technique they used in the US in Pentagon to protect Pentagon against attacks. And this is a two-mixture, very hot polyurea. This is the kind of material that they use to protect truck lead liners against corrosion. So it sticks, it becomes like chewing gum, and it increases flexibility of the member. So we tried that on infill walls. This is unreinforced masonry, and it improved its deformability significantly. So this is supposed to be brittle masonry. As you can see, it flexed a lot. There was no fragmentation. It worked. So we said if it works, then we should probably get more greedy, try to increase its capacity. We provided subsequently reinforcement and then sprayed this on. Here's the failure mode without reinforcement. And here you see blue indicates 23 kPa and failure at 57 millimeters of deflection. When we used spray on polyurea, we went up to 78 kPa. It was able to deflect 254 millimeters without failure. this is showing you application of polyurea on reinforcement. So this becomes reinforced polyurea. It increased bending capacity of unreinforced masonry tremendously while having fragment control of projectiles. And this is after blast. As you can see, the wall carried not only higher pressure, but there was no fragmentation, and it performed beautifully. So once again, if you compare them, as built wall, because it was retrofitted, it carried, it was able to resist 536 kilopascal millisecond impulse. After polyurea, we went up to 2004 times the impulse, and our shock tube was limited to 100 kPa, so we couldn't increase it more. In fact, the wall did not fail, but we ran out of capacity of the shock tube, so it was a very effective way of improving it. Now, another research here is to retrofit timber stud walls. Initially, we were hesitant because nobody would build timber construction for blast resistance. But if you happen to have timber construction right next to a reinforced concrete target building, then they will be subjected to blast. And this is, of course, a very slow motion video, but if you see it in real time, those studs flying like bullets and would likely to kill people. So we developed tension rod system, and then we ended up testing similar wall. One side we retrofitted, the other one we did not. So these tension cables are supposed to provide lateral bracing, just like we did for the braced columns. And here you can see unretrofitted wall did not work, whereas retrofitted panel remained intact. These are stud wall systems. Another research project that we got about $1.1 million from Canadian government to develop blast-resistant window standard, CSA S852, which is companion to this previous standard I introduced. Of course, as you know, glass fragmentation is the first thing that happens into building. The first thing is glass goes, and if it penetrates inside, it would kill everybody because it goes at ultra speed fragments of glass shards. So here's a glazing failure. We put protective film in order to understand capacity of the film. In this case, it wasn't enough. You can see the film ruptured, and then subsequently glass failed, and all these shards flew in, and they all hit the witness panel. So the end result was that thickness of protective film was not good enough. And then we increased protective film. We used different substrates, different walls. This time we have stone masonry because it was supposed to help us understand behavior of historic buildings. And of course, stone being stone, there's no reinforcement. There was failure of the stone in the anchor region. So if your glass is strong, your frame is strong, then it has to fail somewhere. Walls were not strong, so where we anchored them into the wall, they failed. And then we tested walls in steel substrate, and everything worked fine. But then later on, the anchors we used to connect them to steel substrate, as you can see, started failing. Mind you, this is an acceptable failure mode because they did not fly in that well. But this was showing anchor failure. So the first one showed film failure, second one showed anchored zone failure, third one showed anchor failure. Still, anchors ruptured. And then we used another test for reinforced concrete substrate wall, and that performed fairly well. So the lesson is that if you design them, you can make them perform well. We subsequently tested some blast-resistant windows. So what you saw is ordinary windows, ordinary office windows. These are called punched windows. So there's one hole, one window, we're protecting them.